In the final weeks before December 19th, as the interstellar object known as 3I/Atlas approaches its closest pass to Earth, the scientific community finds itself at a rare convergence of preparation, anticipation, and uncertainty. What began as a faint, fast-moving anomaly detected by automated sky surveys has evolved into one of the most intensively observed astronomical phenomena of the modern era. Unlike ordinary comets or asteroids, 3I/Atlas has persistently resisted classification, displaying behaviors that challenge long-standing assumptions about how natural bodies move, rotate, and interact with solar radiation. With less than 3 weeks remaining before the most favorable observational geometry of its entire journey, the world's telescopes, both professional and amateur, are aligning their schedules toward a single objective: extracting definitive evidence about the object's nature before it recedes forever into interstellar space. The importance of this moment lies not in proximity alone, but in perspective. As 3I/Atlas moves along its outbound trajectory, the changing angle between the Sun, Earth, and the object produces lighting conditions that astronomers rarely obtain for fast-moving interstellar visitors. Earlier observations were compromised by glare, shallow phase angles, or limited resolution, forcing scientists to infer physical properties indirectly. December 19th changes that equation. For the first time, shadows cast across the object surface may become detectable, allowing researchers to distinguish between solid structure, diffuse material, and transient features. Surface reflections, thermal gradients, and the geometry of any surrounding debris will be revealed under lighting conditions that favor direct interpretation rather than speculation. In astronomy, such geometry often marks the difference between ambiguity and clarity, and for 3I/Atlas, this window may be decisive. Over the past several months, the object has exhibited a catalog of anomalies that, taken together, form a pattern difficult to reconcile with known cometary physics. Its trajectory shows non-gravitational acceleration without the accompanying gas signatures typically responsible for such motion. Brightness variations occur too rapidly and irregularly to be explained by simple rotation models. The appearance of a persistent sunward anti-tail, material seemingly extending toward the Sun rather than away from it, has defied conventional explanations based on solar wind or radiation pressure. Even the object's rotational behavior appears inconsistent, with pulsations that suggest either complex internal structure or the influence of external forces. Each individual anomaly might be explained away with an exotic but natural mechanism, yet their combined persistence has kept the object under constant scrutiny. As December approaches, the observational effort has become increasingly coordinated. Space agencies, including NASA and the European Space Agency, have scheduled continuous tracking campaigns, while national observatories across multiple continents have synchronized data-sharing protocols to ensure that no critical moment goes unrecorded. High-resolution optical telescopes, infrared instruments, and radio arrays will all be brought to bear, each probing a different aspect of the object's behavior. Amateur astronomers, whose early contributions proved instrumental in flagging unexpected features, are once again playing a role by conducting long-duration imaging sessions using stacked exposures and precise tracking software. Their observations, while less detailed than those from major facilities, provide temporal coverage that professional observatories alone cannot sustain. What observers are seeking during this window is not a single dramatic revelation, but consistency across multiple datasets. Natural objects, even unusual ones, tend to obey stable physical rules. When behavior repeats under different conditions, it becomes possible to model and predict it. Conversely, when patterns shift in response to geometry rather than environmental factors, deeper questions arise. December 19th offers a chance to test whether the object's anomalies persist, intensify, or resolve when viewed from a new angle. If jets change orientation, if brightness fluctuations align with rotation, or if the anti-tail reveals internal structure, scientists will be able to refine their models substantially. If not, the mystery will deepen. One of the most discussed ideas ahead of a close approach comes from Harvard astrophysicist Avi Loeb, who has proposed that the sunward anti-tail may not be a conventional dust feature at all, but rather a swarm of solid fragments traveling alongside the primary body. Under this hypothesis, the fragments would respond differently to solar radiation than gas or dust, maintaining a coherent configuration that appears anomalous under standard comet models. The changing observational geometry of December 19th provides a rare opportunity to test this idea directly. If such a swarm exists, it should exhibit a distinct brightness profile, subtle flickering, or distributed scattering that separates it visually from the main object. It may also maintain a consistent positional offset toward the Sun, a signature that would be difficult to explain through conventional means. Confirmation of such a distributed system would have implications extending far beyond this single encounter. It would suggest that interstellar objects may arrive not as solitary bodies, but as complex assemblies shaped by formation processes outside our solar system. This, in turn, would force a re-evaluation of how planetary defense strategies model incoming objects. Current frameworks largely assume coherent masses with predictable responses to gravitational and thermal forces. A fragmented or swarm-like interstellar visitor would challenge those assumptions, highlighting the need for more flexible detection and response protocols. Even though 3I/Atlas poses no threat to Earth, its behavior is already influencing how agencies think about future encounters. Beyond morphology and motion, spectroscopy will play a critical role during the close approach phase. By analyzing reflected sunlight across visible, infrared, and possibly ultraviolet wavelengths, scientists hope to identify the object's composition with greater confidence. Early spectra have already raised questions, showing an absence of the volatile compounds commonly associated with comets and hinting at materials that may be unusually rigid or reflective. The presence of multiple straight, narrow jets, features that resist alignment with the solar wind, adds another layer of complexity. During December, improved signal strength and reduced interference may allow researchers to determine whether these jets are gaseous emissions, trails of particulate matter, structural edges catching the light, or something entirely unforeseen. The broader context of 3I/Atlas cannot be ignored. Humanity has encountered interstellar objects before, most notably Oumuamua in 2017 and Borisov in 2019, yet both passed through the inner solar system too quickly to allow sustained observation. Oumuamua, in particular, left behind a legacy of debate that continues years later, precisely because the data were insufficient to settle key questions. 3I/Atlas represents a rare second chance, an interstellar visitor that lingered long enough to be studied, revealed anomalies early enough to attract global attention, and now offers a final, well-timed observational window. In that sense, December 19th is not merely a date on the calendar, but a culmination of lessons learned from past limitations. The heightened interest surrounding this event extends beyond academic curiosity. Planetary defense organizations are treating the close approach as a live exercise in international coordination. Tracking a fast-moving, poorly understood object requires rapid data exchange, unified modeling efforts, and clear communication across borders. Drills conducted in recent months have tested these systems under realistic conditions, revealing both strengths and gaps. While 3I/Atlas itself is harmless, the experience gained from monitoring it may prove invaluable when a genuinely hazardous object appears in the future. In this way, the interstellar visitor is serving as both a scientific subject and a catalyst for institutional learning. As the date approaches,